let us say we have an AND gate or a NAND gate that make all other inputs 1 in order to propagate the error to the output of the gate. And if we have an OR gate or a NOR gate, then obviously you would make all other inputs equal to 0. And what about for exclusive OR gate? So you have an exclusive OR gate, you have an error signal coming in on one of the inputs. What would you do? Here you have an exclusive OR gate. You have an error signal coming here. So what would you do so that you can propagate a D or a D bar here? 1, yeah, okay. Any other suggestions? Would somebody say 0? How about both 1 and 0? Because an exclusive OR gate, okay, what will happen? Now let's see. What is a 0 exclusive OR with X? What is 0 exclusive OR with X? So if this is 1, then output is 1. If it is 0, output is 0. So 0 exclusive OR with X is just X, right? So this would be a D, which is fine, because somehow you want to propagate the error. So it is either 0 or 1. Now it turns out that exclusive OR gates are nice because it is easier to propagate error through exclusive OR gates. Now since we have some electrical engineers here, okay, how many of you like exclusive OR gates in your design? Or how many of you, when you design something, if you are, let's assume you are doing some digital design, how many of you try to design something using NAND gates? That's usually a popular choice, or NOR gates, because you can construct everything using them. And exclusive OR gates are a special purpose. So in some special situations, like when you want to check for parity, or in some situations, they actually work very nicely. Although they are not generally used for general purpose digital design, but you will see them time to time. Okay. Now let us look at the idea of single path propagation. So now we want to come up with a method of generating tests. So we can think of this idea that, okay, so what we need to do is to excite the fault, at the site of the fault get a D or a D bar, and somehow propagate it through the circuit. And so one possible idea is to use single path propagation. So create a single path from the site of the fault to the output, and that would give you a test. And the best way to illustrate this idea is to use a simple example. So how about maybe we use this example here. Here's an OR gate, and let's put an AND gate there. And let us assume that we want to get a test from this line, and we could call this line H. stack at 1. And let's assume that the inputs are A, B, C, and D. Now remember, we have a scene1 method, which is the Boolean difference method. And now we are kind of proceeding towards a structural approach. So we want to take a look at the structure and find a test. So here, let's try this. And let's start with excitation. We want to excite the fault. And so since this is stuck at 0, somehow we need to bring a 0 there. And in order to bring a 0, you have to make so we need to use A equal to 0 and B equal to 0, right? So we put 0, 0 there. So this would be a 0, and in presence of a fault, that would be a 1. In other words, we have a D bar at this point, right? Okay, so we have done excitation. And now let us try to propagate the effect of the fault to outside. Okay, so do you see a path to outside? How about, let's try this path. Actually, there's only one path. So if this path doesn't work, then maybe there's no test for it. So, but let's see if we can do it. What do we need here in order to propagate this error to the output of this gate?
1.
We need a 1 here, right? Okay, so we put a 1 here. So we get a D bar, and let's note it down. So so the other AND input is equal to 1. So we got a D bar here. And then this is an OR gate. So let's make that 0. And we get a D bar here. So we get the so we have propagated, but we are not done yet, because we need to justify. We said that this is a 1. Now, how do we know that we can actually make this a 1? Well, I guess in this case, this is easy, right? Because this is directly connected to C. And so let's do the justification. So we have made some choices here, and we have to see if we can justify these choices. So here, C is already 1, so that's not a problem. Okay, we make C equal to 1. Okay, notice that we have made A and B equal to 0. Okay, now we need a 0. How can we bring a 0 there? Let's see. Now, since we said this is a 1, right? We have made this a 1. So we have already made this a 0, right? So this is already a 0. That means it doesn't matter what we have here, this is going to be 0. So we could say D is equal to X, where X stands for a don't care. So that means you could make D equal to either 0 or 1. Either of them will work, and hence the test is Test is 0, 0, C is 1. So tests is, or should I say tests are? Doesn't matter. I suppose I could say test is 0, 0, 1, don't care. But actually I could say either 0010 or 0011, either of them would be good tests. So this is an example of single path propagation. So basically the idea is that excite a fault and through a single path. Now do you think that this method will always work? Why not?
Might have some conflict.
Just if there's a conflict, then sometimes you may find that there is no test.
For example, if that last AND gate was an OR gate.
Oh, you mean this one here?
Oh no, it would still work. No, yeah.
So, but in some cases, it is possible to construct an example. We have to maybe think about it a few minutes. But it's possible to construct an example where a fault is untestable and this method will not work. But in that case, of course, the fault is untestable. Now, do you think it is possible that a fault is testable and this method may not work? And it turns out that, yes, it may fail. And let me give you an example. Single path propagation may fail in some situations, and there is a well-known example. And this is well-known enough to be given a name. Schneider's counterexample. Now in research, a counterexample is a well-known term. So sometimes we make a claim that if it is like this, then it is always this. And so if somebody challenges that theory, then he can disprove the theory by giving a counterexample. Here's an example, and the theory that you have given doesn't work. So this actually is a rather well-known example, and it turns out that it is actually a circuit which is which has some interesting properties. And a while ago we had developed some ideas about something we called testability profile, and we had analyzed some circuits. And this was a very special circuit. It had a very strange looking detectability profile. But anyways, here's the counterexample, and it is a little big. So I need a bunch. I need 4 NOR gates here. So let me first get 4 NOR gates here. And a NOR gate here. Incidentally, some of you may remember that a NOR gate is one of the universal gates. That means you can construct anything using only NOR gates. And I need one more. Now in order, this circuit actually has only 4 inputs. But in order to keep the circuit from getting too ugly, let me imply some of the connections. So it has 4 inputs, A, B, C, and D.